dynamics of inhomogeneous atoms coupled to an optical cavity. I hope you are seeing the main screen, right? Not the.
No, I think the screen is fine. Yeah, we can see.
Yes.
We can see slide.
Can you see the laser pointer?
Yes.
That's fine.
Okay, perfect. Okay, so here is the outline of the presentation. So I'll start with a very basic introduction to atoms coupled to a cavity. And then I'll touch a little bit on superradiance and then speak about how superradiance can be used for lasing using homogeneous. It's still homogeneous because it's easy to solve. We like it and we understand it better. And then we will move slowly to inhomogeneous atomic ensembles. And in the first two cases for synchronization and lasing, it won't be the full-fledged inhomogeneous broadening, but rather atomic ensembles. Let's say you have 10 ensembles with different frequencies rather than atomic ensembles where you have rather than a collection of atoms where the inhomogeneous is a broadening, a continuous distribution. But in the next two, where we have the spin echo, self-stimulated spin echo, and quantum memories, I'll be describing the effects of inhomogeneous broadening in its full glory, where you have this entire Gaussian distributed inhomogeneous broadening. And in all of these cases, the number of atoms are in the order of, let's say, 10 to the power 5, 10 to the power 10. So basically, you cannot think of doing the exact master equation or even Monte Carlo or anything like that. So let's start with the first slide, which is the atoms coupled to a cavity. I'm pretty sure you've seen this a million times. Is the Jaynes-Cumming model, which explains the interaction of a two-level atom with a single optical mode. So this is what the Hamiltonian looks like. Just to revise, you have this energy of the oscillator, the atom, and then there is interaction between the atom and the cavity mode. And if we say we have multiple atoms in a cavity, which is the topic of this presentation, then we can just put a summation sign over here saying that there are n atoms and there are n atoms interacting with a common optical mode. For simplicity, the light matter coupling here is constant, but of course you can make it inhomogeneous. And this is assuming that there is no direct interaction between the atoms. So of course the atoms between these atoms from I is equal to 1 to n, they will be interacting via the cavity, but there is no direct interaction between them, which is like the ZZ type interaction or whatever. Now, there are some examples of experimental setups. It's nice to know, but not constrained to only these. These are just some examples. So the first can be cold atoms trapped in an optical cavity. And these are very clean and might be the examples of homogeneous systems coupled to an optical cavity. And then we can think of rare earth ions, which are basically the lanthanides, for example, erbium, neodymium, thulium, funny names, but yeah, that's how it is, doped in crystals. So they are basically partially filled, they have partially filled 4f orbitals. And if we remember our high school chemistry, the 4f orbital is filled much later than the 6s, 5s, and 5p. But although 4f is located much inside, but n is a principal quantum number of 4, and it is believed that these orbitals will be shielding the partially filled orbitals here from the interactions of the crystal and stuff. And so this make them nice candidates for quantum computing or even two-level atoms. And they are doped in inorganic crystals such as Y2SiO5, and this is just an example. And then of course you have this NV centers or other donor spins in. So all of the systems have their own pros and cons, their own operating regimes. And for example, this let's say rare earth ions, they have this dipole-dipole interaction. So you can excite it to a higher excited state, and they will experience a dipole interaction with the nearest neighbor, which is like super perfect if you want to do some quantum gate. And they are in crystals, so they don't need any trapping like this. So they're already in a crystal, sitting in a crystal, almost room temperature, but they're inhomogeneous. And since it is in a crystal, the crystal already has the stress, strain, and other fields, so they might not have the best coherence properties where, let's say, the cold atoms will be much better. But they all have their own pros and cons. So let's talk about single atoms, what happens when single atoms are replaced by n identical atoms, at least for the first case. So due to indistinguishability and collective response of the atoms to the quantized optical mode, it becomes possible to describe the system as a single quantum mechanical entity. So let's say if you have two atoms, two-level atoms, completely identical, they're close to each other, and they are behaving like a single entity, then the total number of states can be n plus 1. The system can be described as n plus 1 rather than 2 to the power n. And this will become clear here. So if you have two atoms, the ground state would be both the atoms in the ground state. And then the first excited state will be one atoms in the excited and one atom in the ground. But then since it is indistinguishable, you cannot really distinguish which state it is in. And the excited state will be both the atoms in the excited state. So you can see that the number of states becomes n plus 1. So there are 3 states because these two are indistinguishable. And instead of 2 to the power n, which would be the case if you have two independent atoms. Now, something happens because of this and what we know as superradiance. Now, if we remember this angular momentum chapter of our quantum mechanics, when J minus operates on any state, we get this prefactor. And these are basically the decay states. And the ground state is what I showed in the previous slide. Minus J is all the atoms in the ground state, and M is equal to J is all the atoms in the excited state. And apparently, the decay rate depends on the value of J and M is 0 here. And if M is 0 or M is around 0, this gamma effective becomes maximum. What this means is that the decay rate is maximum around the equator. And why I say equator, because let's say in the Bloch sphere, you will represent this as the south pole and all the atoms excited as the north pole or whatever in whichever convention. But if you prepare all the atoms in the excited state and let it decay, so they will start decaying. And the moment they come around this equator, they will decay way faster. So at a rate which is maximum. So this scales as n square. And this leads to a sudden burst of photons due to collective emission, which is known as superradiance. So here is like, there are many experimental evidence of this, and this is just one for strontium laser-cooled atoms, where you can see there is this, the superradiance pulse when all the atoms were prepared in the excited state and they were allowed to decay. And the next question is, due to indistinguishability, they are behaving like a single entity. So they are also emitting in phase. And now when we talk about in phase, the next question comes, can we use superradiance to make lasers? Now this becomes evident, will become evident in some time, but at least what we understand from this figure is that the coherent property or the phase of the emission is determined by the atoms. So coherence is maintained by the atoms in contrast to photons in a conventional laser. But before that, let's revise very quickly what is a conventional laser. So any laser is based on, you have this gain medium where you have at least 3 level atoms, and then you have a metastable. You have another excited state, which has a rate, a decay rate much faster than the state from where it will lase or where the lasing will occur. So you pump the atoms, and then since it has a higher decay rate, it creates a population inversion. And then what happens is that a photon with some phase phi leads to a stimulated emission, and all the atoms come down, and then it releases the photons with a similar phase. But what is important here is that the phase information, they are in phase, they are coherent, that because all the atoms here, or the photons which are generated by these atoms, excited atoms, they mimic the phase of the incoming photon. So instead of that, can we use the phase information of the atoms? Because in superradiance, as we have seen, is the atoms which maintain the phase properties. And what happens in a normal laser, you have this gain medium which generates a pulse, or which has a broadband, which is a much wide broadband, and then there is a cavity which narrows it down, and that is what a laser is. And so is the line width of the laser depends on the line width of the cavity. So what happens is that if this one of the mirror is vibrating, or if it has some fluctuation, you don't get a purity of the laser, because if this mirror is vibrating, you will have some kind of vibrations and impurity in this line width, and that's natural because is the cavity which is determining the line width of the laser. But can we use it in the other way so that the laser doesn't depend on the line width or line width of the cavity, but rather it depends on the line width of the emitters, so that it is independent, it becomes independent of the cavity? And that's why we would like to answer whether how we can use superradiance to make lasers. Now, this is one of the cases. There are references if you want to dive in. Uh, so a bit more in detail. So let's say we have this optical cavity, and then you have a trap with atoms. Eta here is the incoherent pumping, and then gamma, small gamma, is the decay rate of individual atoms. You have this light matter coupling G, everything homogeneous, and you have the decay rate of the cavity, or the line width of the cavity is kappa. And we will be considering that this is in resonance with the dipole forbidden transition of strontium 87. So dipole forbidden because it is not forbidden, but the probability is very low. And we will be using incoherent pumping, which basically means that we'll pump the atoms in principle to an higher excited state, not the one that we are interested. And then this has a much higher decay rate. It immediately decays to the manifold that we want, which is ENG. So any kind of an interaction between the atoms, when you pump it to a higher excited state, those gets destroyed because it decays first. So this is almost like an incoherent, or this is exactly an incoherent pumping. And these are taken into account by the Lindbladian terms like this. Yes, and in this case, the atoms are, let's say, 10 to the power 5. So this master equation or the Hamiltonian is just, it's nice to look at, but you cannot really solve it. So, but how do we solve it? Because of course we can do mean field theory, but we have been talking about coherences. We want to preserve the coherences so that atoms can show or express those coherences in the emission, because we want to make a laser. So we don't want to do a complete mean field, because in a mean field you break all the second order correlation, but maybe we can do something a bit better. But something which is still can be tackled, which is known as a second order mean field theory. So if you have this master equation with the Hamiltonian H, you can write the equation for A dagger A. And you can see that this couples with A dagger A, which is very fine, but then it also couples with A sigma plus. And now there is an n sign, and that's because there are n atoms. So there will be n times, there will be summation n, then I can like write n there. Now to solve this, we need the equation for A sigma plus. Now when we do A sigma plus, we say it couples with many terms. One of the important is sigma plus, sigma minus, but with ij, which simply means that although the atoms are homogeneous, we are still taking the correlation between different atoms. So each atom talks with everyone except itself. So that's why n minus 1 here. But here we can see that it couples with a third order correlation. And then you need to find an equation for this third order. It will turn out it depends on fourth order, and then this game never stops. But we have to stop it somewhere. And what we do is we stop it at the third order. So any kind of a third order correlation, we break it in this form. We are not completely putting it to the correlation of ABC is not A multiplied by B multiplied by C, but rather we preserve it. So in a way so that AB and BC and AC, these are still preserved. And that's how, and then you can get these equations, which can be solved easily. Now we are interested in the laser. So what's happening here is we have this eta, which is the pumping, which is the incoherent pump. And then we have the gamma, which is the individual decay rate, but there will also be a collective decay rate, which is known as Purcell rate. Here, this is given by the gamma C. So in this plot, what I'm plotting is the steady state of steady state photons, steady state number of photons, because if you keep on pumping and the atom also has a dissipation, so the balance of dissipation and driving is a steady state. So it will do some coherent dynamics, and then after that it will settle down on some steady state. And I am interested in knowing what is the photon number in that steady state. And what is shown here in the x-axis is I'm increasing the pump, the intensity of the pump, the incoherent pump, which is eta here. And then on the y-axis, it's n, which is the number of atoms. And as we can see that as the pump parameter is much low, there is no photons there. And that is very normal, because if the decay rates are higher, you can keep on pumping, but the atoms will be in the ground state. But then once it crosses the individual decay rate, which is given by this dotted line, you can see that the number of photons are increasing. It gets non-zero here. This is in log scale. So yeah, and as the pump parameters increases, the number of photons increases, but then after a certain time, it decreases, or it suddenly or very abruptly falls. And that's because you can keep on pumping, but then after a certain time, you reach a saturation. And what that means is that all the atoms are in the excited state, and before they can decay, you're pumping it again. So they basically stay in the excited state and never decay. So you don't get any photons out. So this is this regime. But if you want lasing, we would like to stay in this region where there are number of photons. And we are interested in line width because we want to make a laser. So it's the same thing here. In the x-axis, I have this eta parameter, which is the pumping parameter. And in the y, I am plotting the emission spectrum. So this cavity is emitting, and I'm calculating the spectra of it. And like as before, as long as the pumping rate doesn't exceed the decay rate of the individual atoms, the line width is sufficiently high. And then after that, it starts decreasing. And you can see that after a certain time, it flattens and it reaches the line width of actually much below the line width of the individual atoms, because this is in the range of in the millihertz, and this reaches the limit of the collective decay rate gamma C. So all we can say here is that we can make a laser where the line width depends on the line width of the atoms and not that of the cavity. So in some sense, it's also nice that the fluctuations of the cavity doesn't really matter or doesn't destroy the purity of the spectrum. And just to add here, since I didn't put all the parameters, these are in the presence of decay rates, kappa and gamma are also with realistic values. And this is one of the plot from the experimental group where they have actually shown this lasing with 60,000 atoms of strontium, but then after a certain time, the number of atoms, they couldn't maintain the emitted power because the atoms would leave the trap, and the atoms are lost, and therefore there are no. So what they kind of obtain here is a quasi steady state, but not really a steady state. You can see it's in microsecond, so it's not sustainable. But then what we did was we tried to check if we can inject atoms separately, and will it work? Like if we understand that the atoms are being lost, but at the same time, if we inject new atoms into it by, let's say, with some mechanism, can it maintain the coherence and still preserve? And that can be done very simply by replacing n with another equation of n, and we can just ask the experimentalist that at what rate is your atoms getting decayed or lost, sorry, not decayed, and we can frame this equation, and then you can see that if you're pumping the atoms, we actually have seen that we can recover the steady state in this case. Okay, so now that was the homogeneous case. Now we will move a little bit towards inhomogeneous, but inhomogeneous atoms. But as I said, it won't be. Initially, we'll start with a much simple case. So let's say we have inhomogeneous light matter coupling. Okay, the inhomogeneity can be in various cases. For example, you can have the light matter coupling. The G can be inhomogeneous, but also you have the line width of the different emitters. And this is very natural in rare earth ions, because rare earth ions initially before the doping, you have, let's say, omega A. But then after you dope inside a crystal, you have crystal strains, and there is other fields inside the crystal, each interacting with each other. And then after that, when you do the spectroscopy, you get something like this. Or this is just a schematic, but I hope you understand that you get a broadening that you cannot really control too much. But at the same time, you can also create different ensembles. For example, these are from an experimental paper where if you use the strontium atoms, this F is equal to 9/2 levels, and use a magnetic field, you can split it, and then you can initialize atoms in different levels. So here they have initialized in this 9/2 and minus 9/2 is basically said you can have, like, let's say half of the atoms 10 to the power 5 and half of the 10 to the power 5 here. So you are basically creating two different ensembles of atoms, which are among them are very identical, or rather completely identical. And here they have actually initialized in all the 10 levels. So the peaks are different height because the probability of decay is different due to the Clebsch-Gordon coefficient. So these are weighted according to that. So we'll start initially with a case where we have two different ensembles of atoms. So let's say we have just two ensembles. And we can, just like in the previous case, we can apply the magnetic field, just an example, and this will increase the separation between the two levels. And we can also pump the atoms, and we will be interested exactly in the same thing as in my last figure, which is basically the steady state photon number. Exactly the same plot. On the x-axis, I have the pumping parameter, so I'm increasing the pumps. And in the y-axis, I have this detuning parameter, which basically means as I go up, I am making the two ensemble of atoms. I'm increasing the detuning between the two atoms. So these are becoming much widely spaced in frequency. And what we see here is that initially there are no photons, as in the previous case, but after a certain time, there is in the x-axis, we can see that for certain parameter of pump, we can see there are a lot of steady state photons. But in the y-axis, if we increase as we slowly increase the detuning, after a certain limit, we see that the photon number suddenly drops. And of course, I have tuned the axis here so that it becomes 0. It doesn't become 0. But what happens here is that at this range, both the atoms were actually synchronized. And what it means by synchronization is that both the ensemble of atoms were behaving like a single. And then after a certain limit, that synchronization breaks down and they start behaving as an individual atom. They start emitting in their own frequency. And that's why the photon number decreases. But this can be verified by another parameter here. Like we can check. Let's see if we understand what this means. So this is sigma plus, sigma minus, but between K and K dash. So this is basically the cross correlation at a steady state. So how much sigma plus and sigma minus, how much these two ensembles are correlated, divided by their self correlation, KK or K dash, K dash. And if the atoms were really synchronized, although they have different frequencies, the cross correlation should be same as the self correlation, because it's a single ensemble. And then once they are not synchronized anymore, which is beyond this white dotted line, the self correlation should remain the same, but the cross, how the two ensembles are talking to each other, this should decrease. And actually that's what happens here. So what is plotted here in the inset is the ratio of this, or this divided by this. This is 1, which basically means the cross correlation is same as this self correlation. So it's a single ensemble, and then around this region of for the value of eta, this factor decreases, and that's what actually this is a kind of an evidence that okay, the two ensembles were actually synchronized. And if you are more interested to dive in more detail, maybe the first paper here will be relevant because they have done some kind of a scaling, and because there are two parameters, eta, delta, and also the number of atoms, and they have done some kind of scalings and shown, and from the perspective of a quantum phase transition. Okay. All right, so we move to the yes. So this was for the incoherent drive, but also we can coherently drive the atom. What does that mean is that I have this cavity with atoms. Instead of driving the atoms, which was basically shining light directly on the atoms, if we say it in that way, we can also we can drive the cavity mode from outside, and then the cavity mode instead talks with the atoms because it's coupled. And we can check if there is a kind of a synchronization. And we have actually seen that those synchronization exists. But of course, when we have a transient dynamics, it's difficult to find the spectrum to see if there is a single peak in the spectrum or there are multiple peaks. But of course, when it comes to the dynamics, when we are driving it coherently, the dynamics were also identical. And here we want to know, there was this recent paper here where they showed that we can also use inhomogeneous atoms and we can still get a lasing. So without going into much detail here, let's see what is being plotted here. So you have a cavity, you have atoms which has an inhomogeneous broadening, and they have divided into 31 ensembles where the detuning lies between this parameter, and we can see that here R is the pump strength, and we can see that the spectrum actually shows one peak. Although there are 31 different ensembles, the spectrum reveals one peak, which actually shows that all the 31 ensembles or this different subsets of atoms or collection of atoms are actually synchronized, and they are emitting at the center frequency, the frequency of the cavity. Okay, so this was, in the previous case, we talked about this number of ensembles where we have divided the inhomogeneous broadening into small sections or, small ensembles. But in reality, the inhomogeneous broadening exists in this way, which is basically a distribution, and that can be 10 to the power 10, and so you cannot really distribute or divide it into small ensembles. And in this case, at the remaining part of the talk, I'll be explaining the case, or at least talking about some physics that we get when we have this type of or much more realistic cases of inhomogeneous broadening, especially for rare earth ions or NV centers. We start with spin echoes, which I hope most of you know, but let's revise. Let's say we have this 2-level because we love 2-level atoms, simple. We have G and E separated by an omega frequency. And the same system as before, you have a collection of inhomogeneous atoms, which is inhomogeneously broadened by some bandwidth. And then we apply a pi/2 pulse, and after time t, we apply a pi pulse. So what happens is that the atoms come in phase after time 2t and generate an echo. Now this will become very clear now. Let's say we start with all the atoms in the ground state. There is no I or other subscript, superscript, but let's say all the atoms are in the ground state. They have all different frequencies. And we apply a pi/2 pulse. So what it does is it creates an equal superposition or brings the block vector in the equator. And then we let it evolve for a time t. Now we have like normalized in a way that the ground state is at a 0 level and excited state is at omega. So after time t, the E part will evolve at e to the power minus omega t. And of course, there is no prefactor because we're considering this as G. And then we apply a pi pulse. So what a pi pulse does is a pi pulse takes the state 0 and makes it 1, and 1 makes it to 0. So what it basically does it interchanges G and E. And after a pi pulse has been done, we'll get a state something like this. So G replaced by E and E replaced by G. And now if we let it evolve for another time, this is also known as time reversal type operation because the prefactor in front of E now went before G. So this will now not evolve anymore, but rather this guy will now evolve. And after the same time t, they are in phase. And when they are in phase, they emit in phase and they generate an echo. And this is also shown in this schematic, which I kind of stole from the Wikipedia. So yeah. So you can see the echo. So the first 90-degree pulse or pi/2 pulse creates an equal superposition. It evolves, and then it turns the pancake upside down. And then, which is a time reversal type operation. They start focusing and they focus. Let's see it once again. So yes, so and then it starts refocusing, and after the same time t, it generates an echo. And then we came across an archive paper where instead of one echo, they had like a real train of echoes, like I don't know, 12 or 13 of echoes, and we didn't know how to explain it. Initially, we thought maybe when the spins come in phase, they have a lot of atoms, let's say 10 to the power 10 atoms, which simply means that the coupling, the effective coupling G√n is enhanced. So maybe the echo which is being generated is also absorbed by the spins and creates another echo because that might act as a pi pulse again. But apparently that's not possible because once the echo occurs at 2t, the system is in this phase. Now, any kind of pi pulse will not bring these two components in phase. That's because they are both negative. What happened in the previous case is that we had one negative here, which was ahead in time, and this was a bit behind. And then once we did the time reversal operation, this guy evolved and then catched up with the other one, leading to an echo. But this can never happen with this because these are all at the same place. So if we apply another pulse on this, both will evolve, or this will evolve to 2i omega. So, but maybe something different is happening because the system is completely inhomogeneous. So let's say just a schematic here. Again, you have this yellow line, which is the inhomogeneous distribution. And then let's say you have a cavity line with which is the green. So the cavity is talking to the cavity is coupled to this inhomogeneous distribution, but also there is a detuning, and you are kind of pumping it at another frequency. So there is detuning, there is everything, and they're also interacting with each other via the cavity field. So it's a much more complicated case, but rather than considering that we are doing a pi/2 pulse and pi pulse, let's say that we have these atoms, we have this collection of atoms, which we don't know very well because we know that, okay, it has a distribution of, let's say, 10 megahertz, but we don't know how many exactly are the atoms. And let's say we are hammering the atom with a pulse, just with any kind of a pulse. So what it does is it basically creates a superposition of G and E. We don't know what is the value of A and G. Let it be anything. Let's keep it as general. And then after a time t, the E component will evolve. Now here I have used the superscript J because there are many atoms, but yeah, I missed it in the previous slide, but I hope you understand. And then after another time t, we apply another pulse. But now the second pulse that we apply is not really a pi pulse, because we don't really know what a pi pulse is when you have inhomogeneous atoms. We can find a pi pulse or a pi by 2 pulse for a single atom, but when you have inhomogeneous atoms, you just hit it with something. And then let's say you hit it with another pulse, and what it does, it acts on this and divides us into G and E components. And similarly, it does to the second part. It divides it into G and E with different prefactors. But of course, this matchup, this has to be normalized. But let's say these are any values. And then if we let it evolve for another time t, we can see that the two of the components actually come in phase. And that generates an echo, which acts as a pulse, not a pi pulse or a pi by 2 pulse, any kind of a pulse that can be any fraction of pi, and which will actually split this two again, and this will keep on happening. So this is actually showed in this graph. What I'm plotting here is the evolution of the phases before the E component, which actually evolves, and the G doesn't evolve because it's at 0 frequency. We have normalized it. So this is evolving, as you can see here. And then we apply the second pulse, so it divides it into two. The orange is the E and the blue is the G. And similarly, this pulse also divides this. And we can see that after the time t, this two comes in phase, generates an echo, but this also pushes the spins and this displaces them in the block vector, in the block sphere. And this leads to the other two components, which are basically A1, A2 coming from A1 here, and B1 giving, A giving A1, A2, and B giving B1, B2, which are these components. And then this keeps on going. Of course, we have truncated it here, but there are all these components which are getting in phase after every T, and this generates this train of echo. The nice part is, okay, that's a kind of a hypothesis that we had, but since we are theorists, and which is very nice because mathematically we can see anything, which might not be possible in an experiments. So these are the simulation done with almost 100,000 ensembles, but we do pure mean fill here because we don't need the correlations. And this is the A alpha square, which is the photon number or equivalent to the photon number. And we can see that these are the two pulses, and we see this train of echoes. We don't get as many echoes as the one in the first plot. That's because the coherence, the dephasing rates are much higher in the systems. And what I'm plotting here is the sigma x. So if we say that the spins are coming in phase, we should be able to see it in this plane, and we can say that whenever there is this echo, the spins are actually coming in phase, and whenever they're coming in phase, this is sigma z, which is the block vector or the excitation of different spins. We have so we have plotted basically like 4 or 5, but we can see wherever there is this photon being generated or this pulse that comes out, it pushes the spins in the block vector and maybe in the down or in up, but then it exactly does what we showed in the previous plot. And yeah, and this is the cause why we have this this self-stimulated echo train. And you can also play a bit with the sigma x, sigma y. Instead of using sigma x pulse, you can also use sigma y pulse. So it basically turns the pancake, or by pancake I mean the spin distribution of spins in the other axis, and then it gets echoed in the other direction. So when you see when you measure the amplitude and phase, you can see it as a positive as a negative. So our experimental friends in UCL London actually have done this, and they have shown it that this is actually how it is. But we want to, but okay, so the take-home message from here is that we can use spin echo type mechanism for storing excitations, because whatever excitations we give here, that comes back as an echo. But we also don't want this kind of echo, because if we want to store it as a quantum memory, we don't want it to come in different sections after every time t. But this is also a reminder that if we want to make our system really nice, just by increasing the number of atoms, or increasing or enhancing the G might not be the best case, because this is what happens if there are too many atoms or if the light matter coupling is strong. But can we, in some other way, try to store an excitation and then retrieve it? But here I'm talking about random access. What does that mean is that I would like to store 2 or 3 excitation, but then what happens in this case is that if we store 3, the 3 will come out in the same order, the first in, last out. You cannot, for example, if there are like 3 pulses, 1, 2, and 3 that is stored, and we want the second pulse to be out first, that will not happen with the conventional spin echo. So what we are wondering was, can we do it with some other other technique here. And one of the technique is perhaps the adiabatic fast passage pulses. So worst is one type of pulse. Let's not go too much into detail, but what adiabatic fast passage pulses does is, if you have a inhomogeneous collection of atoms, let's say from -10 megahertz to 10 megahertz, and you apply an adiabatic fast passage pulse, which is a pulse where you chirp, basically means you change the frequency. What happens is that it excites all the atoms from ground state to an excited state. And this will perhaps become clear here. So these are the parameters for the worst pulse, which is white band, uniform rate, smooth truncation. I don't know why it is called worst, but okay. This is the frequency, how the frequency is changed, and this is how you modify or change the amplitude. So if you say a T is equal to, okay, so gamma W is the bandwidth of the worst pulse, and TW is the worst pulse duration. So at T is equal to 0, this goes to 0. So the frequency is minus capital gamma by 2. So this is the frequency that you start, and then at the final TW at the end of the pulse, you can see that this becomes TW gets cancelled, so it becomes plus gamma by 2. So during this entire pulse, you are changing the amplitude, but you are also changing the frequency from minus gamma by 2 to plus gamma by 2. So this is something like that. But you can also change the duration of the pulse. So when you change the duration of the pulse, the chirp rate changes. And what do I mean by chirp rate is the rate at which you are changing the frequency, which is the units of megahertz per millisecond. So in this case, it should be the difference between two will be gamma W megahertz divided by the time, in how much time this was changed. So this is R. And when we apply this type of pulse, again, I am not going into the detail, but let's trust me, and please trust me. And if you want to know how this is derived, there is the paper here. The phase that each of the atoms actually acquires looks like this, where R is the chirp rate, delta is the detuning, T naught is the center of the pulse. And yes, so there are terms which depends on the detuning of the spins, which is fine. But also there are terms, for example, this one which depends on the chirp rate. What does that mean is that if you excite the atoms from ground, or if you excite, so if you excite all the atoms in an inhomogeneous broadened collection of atoms from ground to excited, the spins will acquire, or the atoms will acquire phases based on their detunings, which is completely fine, but it will also acquire a phase which depends on the chirp rate. Now, if you want those atoms to be refocused so that we can get the memory out, you need to give the same phase back by you applying the same chirp pulse, because otherwise they won't come in phase. And we will use the same principle for storing multiple memories. And this is from a simulation. This is a numerical results where firstly, I have this small excitation that we are injecting. And then here is a pulse A, which has a chirp rate, which I don't recall, but it's different from B. And then between A and B, so what we understand from the previous equation is that once the chirp has been applied, we get this type of phases. So after here, the spins has a phase which depends on the chirp rate of this pulse. And now we put in one more excitation. So these are our two excitation that we want to be retrieved. Now, after that, we apply a pulse, another pulse B, which is another worst pulse with a completely different chirp rate. Now, if we want to recover this excitation has already B phase incorporated in it. Now to nullify this phase, we need to apply a B pulse again, as I explained before. And once we apply the B phase after the same time, it spits out this excitation. But the phases which has been acquired from A is still there. So this excitation is not going to come out unless we apply another worst pulse A. And that's what we do it here, and we get it back. So this, if you're interested in more detail, this was an experimental paper where our collaborators from UCL actually did the experiments and we did the theory for it. And this is also in the viewpoint, a very general, not in technical details, like a viewpoint which has been published. So might be interesting to look into it. And I'll stop here. So what I have actually done is given, rather than going deep dive into individual thing, I've given kind of a appetizer of different things that can be done with atomic ensembles, homogeneous, inhomogeneous, or even different ensembles with like 4 or 5 or 10 ensembles. And I'll acknowledge here Klaus was my supervisor. Most of the work has been done during the PhD, and also John Morton and his group for self-stimulated echoes and random access. They were the experimental collaborators, and we learned a lot from them. But I'll thank every one of you for your attention. I think I'm done much earlier, but that's nice, I believe.
Yeah, thank you, Kamanasish, for the wonderful talk. Yeah, personally, I have a lot of questions, but I think I'll keep them for later. So I'll open it to the audience, and please, you can ask your questions directly to Kamanasish. So are there any questions?
Yes, I have a question.
Yeah, please go ahead.
So in one of the slides, where you are applying pi by 2 pulse and evolving it for time t and applying the pi pulse again. So here you were saying that echo, whatever it is, it can't be explained if it's like it's not that the pi pulse is again acting after this last evolution for time t, right?
For time t, yes. So just to be clear, you were asking about the slide, right? Yeah. So what happens after this pi pulse is basically it turns the pancake, which basically means 0 becomes 1, 1 becomes 0. And now if let it evolve after time t, both these two components comes in phase. And then what happens is that, and this is independent of the detuning, because they are all the spins will be precessing with the same detuning. So it means all the spins are in the same phase and they are emitting in phase. And that's why we get the echo. Otherwise, in the normal case, they emit in different phases and they, on average, they cancel out. I hope I'm clear.
So after that, like after time t evolution, suppose if the pi pulse is acted upon it, so again the E and G state they interchange.
Yes, right? Sure. Yes,
and
the E and G will interchange definitely, but the thing is you have to apply more pulses manually to create this effect, because these are now already together. Initially, they were like one guy was ahead, and then you applied a pi pulse. So the other guy caught up, but here both are together. So let's say the echo actually was a pi pulse. It has made it E becomes G and G becomes E. You'd still have to apply one more pulse to like drag one behind and one forward. So this cannot happen without another manual pulse. Yeah.
Okay. Okay. So again, in the atoms, suppose like n, say 2 atoms or more than more atoms inside a cavity. So you were saying effective number of states will be, suppose there are n atoms, now the effective number of states will be n plus 1.
Yes, so that was the case when you have this indistinguishability or kind of a decay kind of a states. But here, let's say if for this case, just for the spin echo, you don't even need a cavity. Let's say you have just a collection of atoms and you are applying pulses on it, it will still work. I mean, the cavity doesn't do anything here, at least. But of course, when you do the experiments, you might need the cavity for collecting the emission, because you might want to, you need the directionality. So the cavity will give the direction for detection.
Okay.
So yeah, but this is irrespective of the cavity.
Not that one.
And these are not identical atoms. These are like different atoms. So this omega here, I apologize for, I should have like written omega I and summation sign. So these are like all the atoms with different frequencies. They are all precessing at their own frequency, but irrespective of this omega, they all will come in phase after this time t. So that's the take home message here.
Okay. So the indistinguishability is the earlier part you were saying atoms inside a cavity. So you're saying but the indistinguishability comes like when do we say?
Yeah, so let's say you have cold atoms. Let's say if I can find it here, let's say, yes, exactly. It's a schematic. Again, I'm scared to put experimental plots and then explain it wrongly. So I put a schematic, which is much more easier. So let's say you have the strontium atoms here. and they are all at the antinodes of this of the standing wave. So they have identical G, and all the atoms are the same. So this is an example of identical atoms. But let's say you have rare earth ions, which is like this. So the before you doped it, it was omega A. After you doped it, you got a mess like this. So this is like a collection of atoms, but completely inhomogeneous.
Okay.
Yeah.
Suppose if you have two atoms inside a cavity, and say one is coupled G like +1 and the other one -1, like so it's like the minus state is coupling to the cavity, you can think of.
Yeah.
Like, so even in that case, it is say suppose if you are taking the system to EE, that excited state, and this minus state is coupling to the cavity. And do you think even in then the transitions occur like from EE to minus to GG, like even then
like which transitions like are you talking about? Like the is this like related to the spin echo or
no normal optical transitions?
The transitions, okay.
From EE state to via minus state to GG state, like though the atoms are in out of phase.
I mean, it has okay, so I really cannot relate it, because if you have two atoms, so there is, I don't like, where is this phase coming from? Because if it is allowed by the transition rules or the way you couple your levels with the cavity, there should be nothing is preventing it from coming down, right?
Like one is the G coupling constant for one atom, say, is +1 and the other is -1. Like one is coupled at node and one at antinode. Like
Okay, so
then
so you are talking about this case where yeah, so let's say, okay, yeah, so this is basically an example when you have like a different coupling rate, right? So yeah, I mean, I won't be able to, maybe I need to like have a look like what happens for a single atom case. But like if you have a collection of atoms, like 10 to the power 10 atoms, and in principle, like not all are at the complete nodes and there will be collisions. So in general, G is inhomogeneous. So it's not really coupled exactly with the, yeah.
So just if we have just two atoms.
Yeah, to be honest, I don't recall the energy levels and with the when it is coupled with the cavity, but yeah, we can have a look maybe.
Okay.
Yeah, it's difficult to recall suddenly this. Yeah.
Okay. Thank you. Thank you.
Okay, yeah. Are there any other questions?
Hi, Kamanasish. So I have a question. Do you think mirror fluctuation in the cavity or the cavity field can be modeled as a dephasing?
Can be modeled as a dephasing? Yes, exactly. That can be modeled as a dephasing, and I think in this
But
paper,
I think you have not included in the linear form of your equation.
Sorry?
I think, but you didn't include that part in your master equation.
Yeah, so I didn't. So okay,
you have like sigma z and sigma minus.
Yeah, sure. But in this case, like yeah, I have, in this case, we have this dephasing of the atoms, but in principle, the spectrum is independent of the cavity. So what cavity does is, so if you didn't have the cavity, the atom will be like decaying and releasing the photons in every direction, right? But you want to capture this, so you need a cavity. So cavity does only gives a directionality. That's it. It's in a bad cavity limit. So the mirror fluctuation doesn't matter in this case. And that's the best part of superradiant laser, that it doesn't depend on the cavity, fluctuations. So that's the main motivation why we want to use superradiant and not the conventional laser.
Oh, okay. In the superradiant phase of your diagram that you uploaded, so did you see any like log A diagram more than 2? There is a
yeah, there is. So this is log. So this is log means this is 1.
Okay.
So there,
square like.
Yeah, so there are more. So that's why we call it superradiant lasing, because there was kind of a terminology in the literature, like depending on the number of steady state photons. Yeah, but the original proposal, the first proposal, which was a kind of at this article here. Maybe you should also be interested to look into it. So they have less than 1 average photon. So it's not really a stimulated emission kind of a thing. So because the phase is being encoded in the atoms. So yeah.
Okay, thank you.
Yeah, we can take maybe one more question from the audience.
I think there's a raised hand, but yeah, please go
Yeah,
ahead.
Ranjit, please go ahead.
Thank you for delivering a nice talk. I have 3 questions, but I will ask one. So, since there is a restriction,
no, we have time. I think you can quickly squeeze in all 3.
Okay,
Yeah,
thank
yeah,
you.
please.
Thank you. So, did you study behavior of noise over the time? Because noise level, sometimes magnitude, I mean, of noise become more than mean value.
So, okay, I think I don't understand what you mean by MOS or
noise. Sorry.
The
variances.
So, do you mean the cross correlations?
Like in one of your slides, you yes. So here you have shown the average or mean values of number of photons. So
yes, like in this plot, right?
Yes.
Yes, so we did study these values also, actually, and I didn't present it, didn't want to be too technical, but yeah, but I think in this, not in this one, at least in the synchronization thing, yeah, in the second, it's already there. So we have plotted it, the sigma plus, sigma minus, how the cross correlations are changing.
Mm-hmm. Okay.
So, yeah.
Thank you. Second question is, in quantum second revolution, manipulation of each atom is more preferred as compared to the ensembles. So my question is, do you have any plans to manipulate interaction of each atom with its environment or neighbor, and then study quantum entanglement and how to reduce noise?
So in which case, like, do you mean in the lasing case?
Yes, in the lasing.
So by interaction, do you mean that do we want to like kind of change this Lindbladians and engineer some different?
Yes.
Yes, I mean, but there should be some motivation why to do it. Like if there is a motivation that, okay, we can get rid of something using this. I mean, what I understand from now is it's mostly an experimental challenge now, because this works perfectly. But if we look at this graph, they are losing the atoms. So, and if they can somehow have a conveyor belt where they are bringing in new atoms as the atoms had, so this will work perfectly. At least that's what was the hope from, and that's what I heard from the experimental group, that they were that ambitious about it. But again, sure, there might be some new physics coming up if there is a new type of, if you engineer the bath in a different way. But yeah, I am not aware, or yeah, but I agree.
Thank you. Last question. Could you please name of the software packages you use to model 60K, if I understood correctly, atoms?
What atoms, sorry?
Huge number of atoms.
Yeah. Okay, so in this case, yeah, so this is a lasing case, and we are incoherently driving. That helps a bit, because if you are driving it incoherently, the average values of A, sigma plus, sigma minus, these are all 0. So you are left with simple number of equations that can be solved. But then in this case, when you are like inhomogeneous atoms, like in this case, you have a cavity, and then you are driving all the atoms. Let's say I didn't plot the figure again here. In this case, I have 220 ensembles, and it scales as n square, because all the ensembles are also talking to each other. So sigma plus, sigma minus, this term basically. It scales as n square, and then it becomes really, really difficult to integrate those equations. And in this case, what we did is this was we wrote the code in and parallelized it in GPUs. And that was, I think, the first and the last time I have done that. I won't do that again. But yeah, so yeah.
Sorry, I was not close to my microphone, so I will repeat once more. So could you please name of the software packages you use to model your model?
Yeah, so I used, this was actually parallelized on GPUs written in C.
Thank you.
So you can maybe try MATLAB, but I'm not sure, because you have to like wait till steady state. So if you want to do for like many atoms, so yeah.
Thank you.
Yeah.
Yeah, Ranjit, to the reply, like a lot of these codes are so you'll probably have to.
Yes, but I think like I think I have uploaded all of these in the archive or in the GitHub. So if you go to the archive paper and the code, they should be available. And if you find an plus minus error or something, let me know. Sharing codes is also sometimes scary, you know.
You can also use, I think QTIP is a nice Python library for studying cavity QED and light matter.
Did you say QTIP?
QTIP, yeah.
Yeah, but in QTIP, you solve the master equation, right?
Yeah.
Yeah, but yeah, I mean, if you have less number of atoms here, we were solving this mean field equations or the semi-mean field kind of a thing. So yeah, there is a question. Okay.
Yeah, so I wanted quick.
Yeah, it's breaking your voice. Can you repeat? Sorry.
Oh, sorry.
Or maybe it's my internet.
Hello.
Hello. Yes.
Yeah. Can you?
Yes, I can hear you, but like it's a bit broken. But I also don't know. Is it like my problem or is it your internet?
No. It could be from my laptop's been acting a bit strange. So I'll just speak slowly.
Yeah.
So superradiant laser you can also see with few atoms, right? You really don't need to go to very high number of atoms. Is it true or?
Yes, I mean you will be. But okay, the question is like how many is less atoms and how many is more atoms?
So what I mean is, can you go to a smaller number so that you can use permutational symmetry to exactly solve the system rather than go to mean field?
Yes, I mean the principle should exist, right? I mean, if you can solve the decay model with like 20 atoms, or maybe like with the Monte Carlo, you can solve it for maybe 40. I think the principle should be visible.
No, I mean, you can use permutational symmetry, right? Since they are identical atoms, permutational symmetry will allow you to.
Yes, but Himadri, I'm honestly, I'm not aware of that actually, so I won't be able to answer that. But all I remember is we had a postdoc in the lab who did it for like, I think 1000 atoms using some kind of a symmetry.
Okay.
So maybe you can look into it. So his name was Yuan. So maybe Yuan Moelmar, you should be able to find it.
Okay. Thanks. Yeah. So okay. Yeah, I'll look into it. Okay, so let me thank Kamanasish for the wonderful talk. Can you hear me, all of you?
Yes.
Okay, thank you so much, Kamanasish, and all the best. We move on to the next speaker. Sir Rangit Bhattacharyya.